Lesson 2A. Please follow along in the notes packet. From Lesson 1, we talked about the area integral connection. That was Lesson 1A. And then in Lesson 1B, we talked about the evaluation method, or the thing that is only minorly important, the fundamental theorem of calculus, part 2. Very, very important. There are two ways to show the evaluation method. We can say that the integral from a to b of f prime of x dx is going to be the antiderivative of f prime, which is regular f, at b minus the antiderivative of f prime at a. Other authors like to write it like this. They say that the integral from a to b of regular f of x dx equals, again, the antiderivative. This time they express the antiderivative as big F, so big F at b minus big F at a. Now let's take a look at part C, the fundamental theorem of calculus part 2 applications. There will be two kind of subsets of that. The first one is C1, and that's going to be the focus of this video. Displacement, position, total distance. Let's start off by calling x of t the position of some particle along the x-axis at time t. So position on x-axis at time t. Okay? Now you should know that the derivative of position, the rate of change in position with time, is the velocity, which we've discussed earlier in the course. So now if I ask the integral from t equals a to t equals b of v of t dt, then using our fundamental theorem of calculus part 2, we would clearly say, maybe think it in your head what the answer would be. Hopefully you're thinking x at b, the antiderivative at b, minus the antiderivative at a. Let's talk briefly about the words displacement, position, and total distance, and I'm going to attempt to show you this in this simple diagram. Let's have a particle on the x-axis, and let's say that particle starts at the starting position of x equals 1. That's for t equals 0, x is equal to 1. That is our starting position. Now suppose the particle does this. It moves to the right, 1, 2, 3. And then the particle moves to the left, 1, 2, 3, 4, 5. And this is where it ends up. So there are three things we're going to look at. One, what is the position of the particle? Well, the final position of the particle is at x equals -1. What was the displacement of the particle? Well, we started at 1 and we ended up at -1, so the displacement would be a -2. But the final question I will ask is, what is the total distance the particle traveled? And that would be, well, we moved to the right, 1, 2, 3, and then we moved to the left, 1, 2, 3, 4, 5, so the total distance is 8. So three distinct things to look at. Displacement in this case was -2, position in this case, the final position was -1, and the total distance was 8. All of those have very distinct answers. Now we're going to develop these ideas a little further on the next page. Some items to review. We have that the particle's moving to the right when the velocity is positive. That's a review from previous parts of the course. Acceleration is positive when the derivative of velocity is greater than 0. And then do you remember the particle's getting faster, or we could say the speed is increasing, when both v of t and a of t share the same sign. So that's the review part. Now we're going to look at this displacement, total distance, position as they relate to the definite integral. So now we're going to look at this again, the integral from a to b of v of t dt is going to equal x at B minus x at A. The position of the particle at B minus the position of the particle at A. Can you tell me in words what that represents? I hope you're thinking displacement. And you might be thinking displacement of distance over the interval A to B. See, in our illustration, our position at B, our final position was -1, and if I take away the initial position of +1, then that would give me a displacement of -2. If I want to define x of B alone, well, mathematically, I want to take the equation here that we already established, fundamental theorem of calculus part 2, and I want to solve this equation for x of B. So you see, all I have to do is add x of A to both sides. So I'll have x of A plus the integral from A to B of v of t dt. So that's mathematically what it equals. What does this equal in words or in context? Well, this is the starting position. This here we just described as the displacement. So you take the starting distance plus the displacement, and that's going to give you what we already defined, the position or final position of the particle at time t equals b. So we have displacement, we have position, and the final one is total distance. Total distance from A to B. So let's see if we can't work backwards to say the math that would lead to the total distance. So how would that work? Well, we know in our illustration that the answer was 8. That was moving to the right 3 and to the left 5, but we didn't really consider moving to the right was positive and to the left is negative. We just looked at it, each one, as its absolute value. So if you're thinking that this should be the integral from A to B of the absolute value of v of t dt, then you are correct. That's going to give us the total distance. But what I want to do is break this down. I want to say this is going to be the integral from A to C of v of t dt minus the integral from C to B of this v of t dt. Let's see if we can illustrate this graphically. This will be a graph of velocity to time. So the velocity is above the t-axis, and then the velocity is below the t-axis. And if you recall, let's just write this, y equals v of t. And if you recall, when the velocity is above the t-axis, the particle is moving to the right, and when the particle is beneath the t-axis, it is moving to the left. So let's call this our starting point, time A. This is our ending point, time B. And then at some point, the particle is at rest because the velocity is 0. So that's why I like to break up the integral that way, where we can call the integral from A to C our positive displacement, and the integral from C to B is our negative displacement. And if we then subtract the negative portion, it would make it positive. So like an illustration, we could say that the integral from A to C was equal to 3. That's the integral was positive 3. And then the integral from C to B was, let's say, a -5. Not the area, but the integral was -5. And if I wanted the total distance, I would have to take the 3 and then subtract the -5 to get 8. So here it is, total distance. One of the ways you can think about it is total distance is equivalent to what we find when we find the area. And then displacement is equivalent to what we find when we evaluate the integral, which, if you recall, is sort of like net area. Displacement is the integral, total. For the examples, we're going to use technology, so please have your calculator ready. Please make sure it's in radians, and we will then begin the lesson examples. Okay, example 1, an object moves along the x-axis with initial position, x of 0 equals 2. The velocity of the object at time greater than 0 is given by the function. Before anything else, let's get this into our calculator. So we want to go to our calculator. Let's go y1. And let's define y1 to be the velocity function. So that'll be the sine. Now, of course, it is in terms of t, but when we enter it into our calculator, we are going to use x. So we'll enter the pi divided by 3, and then we're going to multiply it. That's times. We're going to multiply it by x. We have to use x in the calculator, even though it really is t. So take a moment and graph that. Make sure you graph that on the domain 0 to 4, the window setting 0 to 4, because the problem is talking about everything happening between 0 and 4. Once you have that graphed, which should look something like this, it goes above the t-axis and then below the t-axis. So once you have that graphed, I would like you to find where the particle is at rest. Even though I'm not answering any of the questions A through D yet, it is good practice to find where the particle is at rest. You don't need a calculator to do this, but I want you to practice the keystrokes to find the 0. And that includes F5, 0, lower bound to the left, upper bound to the right. That 0 equals 3. But there's also another 0 over here at 0. Here is what we must write. We have to indicate that the velocity, and I'll just describe it as v of t. I don't have to rewrite it. I'll say v of t equals 0 at t equals 0 and also t equals 3. That's all that I have to write. Now we're ready to answer the questions A through D. Question A. What is the total distance traveled by the object over the time period 0 to 4? So our total distance, if you recall, is going to be the integral from 0 to 4 of the absolute value of our v of t function. But what I want to do, like we showed in the beginning introduction, we want to break that down. So this is going to be the integral from 0 to 3 of v of t dt, and then we're going to take away a negative quantity. That negative quantity that we are taking away is the integral from 3 to 4. Because it's below the t-axis, the integral from 3 to 4 will be negative. So I'm going to subtract the negative integral, because our total distance will always be positive. Again, this is very much like finding area. So I'd like you to evaluate that on your calculator. Your answer may come out to be on your calculator 15 over 2 pi. That's the exact answer. If you press diamond enter, we will get the decimal equivalent of that, and that's going to be 2.387. Now the question doesn't ask for units, but let's pretend that we have meters and we have seconds, so the units on the total distance would be 2.387 meters that the particle traveled. Part B, what is the position of the particle at time 4? So what we're asked to find is the position of the particle at 4, x of 4. So the position of the particle at 4 must consider where it starts from. This diagram is only the velocity, but the diagram does not tell us where the particle started. We need some other information, and that information is given here in the problem, that x of 0 is equal to 2. The way that I will write it is x of 4 is equal to x at 0. This tells me I'm considering the starting position, plus I have to then add to it the displacement, which is going to be the integral from 0 to 4 of velocity. The displacement is allowed to be negative. In this case, the displacement won't be negative because there is more area above than there is below. The starting position was 2, and then again the integral from 0 to 4 of v of t dt will be evaluated in the calculator, and that comes out to be 3.432. Units on that, well, if I'm talking about an x-axis and I'll say what is the position of the particle, you may say it is at the 3.432 meter marker. Just a placeholder. In part C, the question wants us to find the average velocity. Now, keep in mind that the function that is given is the velocity function. So velocity function is given, and they want the average velocity. What they really want is the average velocity's value. Remember, there's a difference between average value and average rate of change. In this case, even though velocity is a rate of change, it is the function they gave us, and so it's the average velocity's value. And the average value is going to be integral over interval. So it's going to be the integral from 0 to 4 of v of t dt divided by the interval, which is 4 minus 0. Oftentimes, authors will write it as 1/4 times the integral from 0 to 4, v of t dt. In our calculator, that comes out to be 0.358. And the units on that would be velocity units, so that would be meters per second if those units were provided. See, the numerator would be in meters, and the denominator would be in seconds or time. Finally, in part D, it wants to know what is the average acceleration. So velocity is given, and they're asking for average acceleration. What they're really asking for is the average rate of change of velocity. So the average rate of change in velocity. And the average rate of change, if you remember, is the slope of the line connecting the endpoints of the function. So we would need change in y over change in x, you might say. So we would need v at 4 minus v of 0 all over 4 minus 0, the average rate of change in velocity. And that's going to come out to be a negative 0.217. That negative should actually make sense, because if I'm finding the average rate of change of this velocity function, then it's going to be equivalent to the slope of the line connecting the endpoints, and that slope is clearly negative. Units on this would be meters, and it would be per second squared. The numerator would be meters per second because it's velocity, and the denominator would be seconds. So meters per second divided by seconds, meters per second squared. I would like you to try example 2 on your own. Just a couple things to note: that this negative symbol should not be a minus but a negative. So if I let y1 equal a negative x plus 1, and also if you remember, if you're multiplying a polynomial to a trigonometric function, you want to insert the multiplication symbol. So make sure you enter it this way. And also, let's graph this on the domain 0 to 3. So try this problem, press pause, and when you unpause, I will have revealed the solutions. Okay, so here are the solutions. A couple things to point out. We must say that the velocity equals 0 at the times that we found, so that we can use that in our integrals. Also, this graph starts off negative. The velocity starts off negative, being below the t-axis, so we have to indicate that by minus. So we start off with a minus a negative integral to give us a positive quantity. Another thing I wanted to point out is I could have done this in the first example. I didn't. I'll show it to you now. Since I have this into y1, the easiest way to get this quantity isn't necessarily with the graph, but in the home screen, I can simply call up y1 of 3 minus y1 of 0. That will give me the numerator. Then I can take that answer and divide by 3. or I can insert an extra set of parentheses and divide by 3. That will get me my answer quickest. The last example, example 3, is actually a real AP question from the year 2000. It was question number 2. In this question, we have two runners. One runner has a velocity described by the graph that you see. The other runner has a velocity described with a formula. I would like you to try this problem in its entirety. Then I'm going to discuss it. Press pause now. Question A wants to know what is the velocity of each runner at time 2. So, for runner A, the velocity at time 2, well, we need our graph in order to get this. So at time 2, I literally just want to know what is this point on the graph. In order to do that, I must first come up with an equation for this line segment that starts here and ends here. That should be a simple equation. Y equals mx plus b. The slope would be the change in y over the change in x, which would be 10/3. So this equation is simply y equals 10/3 t. Then, if I wanted to know what the velocity was at 2, then I would plug it in and I would get 20/3. So the velocity of runner 2 is equal to 20/3. The units on that is meters per second, and that is a point on the graph. For runner B, the velocity of runner B at time 2, well, what we want to do in this case is we want to enter our formula into the calculator. Let's call it into y1. So I then just need to compute the velocity at time 2, and that should come out to be 48/7 meters per second, and that was using the calculator. Again, in the home screen, if that was in y1, you just simply need y1 of 2, and then the answer is revealed. Now in question B, they want the acceleration of each runner. So the acceleration of runner A at time 2 would equal just simply 10/3 units, meters per second squared, and that would have been found by the slope of the graph. Slope of the graph. Then runner B, the acceleration at time 2, we would use our calculator to get that, and that would be 72/49 meters per second squared. That's using the calculator. Maybe some details on that. What I would do from my home screen is the following. I would call up the derivative of y1 of x with respect to x and parentheses. But before I press enter, I'm going to press the slash key. The slash key means such that you will find this, I believe, right above the equal sign. There's a slash, and then we're going to say slash x equals the value of 2. So in one line on the calculator, that will help me return the value of 72/49. And as I just looked, it appears as though that slash button is just below the equals. So this slash here is below the equals. Make sure that this equals is actually the equals button. Finally, in part C, the question wants to know what is the total distance traveled by each runner. So for runner A, the total distance equals, in total distance, we don't care where they started, we just want to know how far they went from wherever they started. So the total distance is going to be the integral from 0 to 10, the absolute value of v of t. See, I just get so used to writing absolute value for total distance, but it turns out in this case, since the velocity curve for runner A is always above the t-axis, the velocity will always be positive, and there is no need for the absolute value, v of t dt. And as you can see, I've kind of scribbled some geometric shapes above, because the way that I'm going to find this integral is to appeal to geometry. I've got a triangle which I've shaded in purple, And the area of that triangle is going to be the base of 3, the height of 10. That's 30 divided by 2, so that's going to be 15. And then we have that rectangle shaded in red, which has a base of 7 and a height of 10, and that will be 70 to give me the area or total distance of runner A to be 85 meters. That's appeal to geometry. Now for runner B, the total distance is going to be the integral from 0 to 10. Same idea, the absolute value of v of t dt, but runner B's velocity is also always positive, so I don't need the absolute value. I evaluate that on my calculator to get 83.336 meters. That's done on the calculator. And that is the end of lesson 2A.